Hello everyone, this is the final lesson on this theme of magic and similarity. A priori, I want to write straight away that this is a fun class and it is based on two wonderful presentations of a great idea one by George Polya in his book, the famous Hungarian mathematician, in his book, The Mathematical Methods in Science. Very wonderful and readable book, and I shall attach a copy of this book in my Google Classroom. And the same idea is presented by Late Professor Tom Apostol of Caltech, who made a series of TV episodes on project mathematics, and one of the episodes is based on today's lesson, project mathematics. I shall also give a link to this particular episode on my Google Classroom. So what's the theme, or what's the idea that they have discussed? It is famously known as the Tunnel of Samos. Now this is a true story from the time of the great Greek mathematicians, and how they solved a very wonderful problem using basic geometry in which they were really good. So before I get on to the story, I just want to tell that the solution by Polya is slightly different from the solution presented by Professor Tom Apostol in his TV presentation. So I shall discuss the solution of Polya, and the reason for that is his solution is based on similarity, which is our theme of all our lessons right now. And what I really want you to note is how similarity is directly associated with real life problems. So this is the real emphasis of today's class. It solves real life problems, and you will meet it, this idea of similarity, you will probably meet it throughout your lives. And what I really mean by that is similarity is basically symmetry, and symmetry will play a big role in many of the solutions of the problems you're going to learn and also solve yourself in the future. So with this as the background, let's get on with the problem. See, the problem is very nice and simple to understand. So there is a mountain, and on one side of the mountain is a very prosperous city, and on the other side of the mountain there happens to be a huge water body. Now you can expect that this very prosperous city will eventually run out of water, and now they really want to access the wonderful water body that is on the other side of the mountain. So this is the problem, and how do they propose to solve this? They propose to solve this by building a tunnel through the mountain into the water body, and this is the tunnel that they wish to dig. Now the tunnel is fairly long and involves a lot of work, and to cut short on the time, they decide that they're going to dig simultaneously from both sides of the tunnel. Right. So here's the first problem. The digger A and digger B cannot see each other. So how do you ensure that when they dig and meet, they will meet and they will not miss each other? So that's the first part of the problem. How and which direction would they dig to make sure that they meet? The second part of the problem, which is less important, is they do not know exactly how much length they will have to dig so as to get an estimate of the amount of time that is required to build the tunnel. Now the second problem is less important as compared to the first problem. As it turns out, they have solved this problem in a very beautiful way, and not only have they solved the problem, they have built the tunnel, and that tunnel is famously known as the Tunnel of Samos, and it still exists in Samos. And in Professor Tom Apostol's episode, the shooting is done on site in the island of Samos, They actually go there and show you the tunnel which still exists. So that's the background. Now let's see how they have solved this problem. So before I start, okay, I shall discuss only Professor Polya's solution, and this solution is based on similarity. So once we get the fact that it's based on similarity, the solution is fairly easy to understand. So now I shall draw the top view of this problem just to give you an idea of what's happening here. So you have the top view of the mountain. This is the top view of the mountain, mind you. So there is a mountain here, and then there is water on this side, water, and then there's a city on this side which is like this. Now the first step of the problem is to find a spot where the person, the people who are actually at work, can actually see both the water and the city. So they walk away and try to find a place in which both the city and the water are visible to this person. So that's the spot. Let's call it A, and let's call this point as B, and let's call this point as C. Okay, so as you can see that there's a triangle that is involved, but now what I shall do is I shall go back to my first picture. Should I just go back to the previous page? Okay, so go back to the first picture, and now you know what's happening. Point has been discovered where both the city and the water are visible. So now let me just make some space here and show you that point ABC that I talked about in the previous picture. So here's this point A, and both these points, water and the city, are visible. So that's where we are. Now because they're visible, okay, let's call this B and C. So now AB and AC are measurable. So this, for the sake of some numbers, let's say that AB turns out to be 5 kilometers. All right, so let's say this is 5 kilometers, and let's say that AC turns out to be 3 kilometers. Right, so this is 3 kilometers. Now it turns out that we can find a way to find the value of BC. Okay, it's possible to find the value of BC. Now let's say that we find the value of BC. So that's one half of the problem solved. But more interestingly, we'll be able to find out angle B and angle C as well. So I just want you to note that if these three things are now known, then what does it mean? So you know this angle and you know this angle, which means that this guy here knows the direction in which to dig, and this guy here, B, also knows the direction in which to dig, and therefore they will meet each other. So that's the implication of finding out the values of BC, length BC, angle B and angle C. So the only thing to discuss now is how do they figure out these three quantities from the triangle that has been marked. So here it goes. They cut down BC by some fixed ratio. So let's say by a ratio of 100. So what was 5,000 meters by factor of 100? So 50 meters. So they mark a point B dash at 50 meters from A. So I'll just write down here, everything is cut down by a factor of 100. So you can see that we are inching towards similar triangles by bringing down the big triangle to a size of 100th. So I mark B dash, which is 100 5,000 divided by 100, that's 50 meters. Now similarly, I mark this point C dash in such a way that AC is 30 meters. So you can see that 3 kilometers has been cut down by a ratio of 100. And then what they do is they mark, I think I messed up in the diagram slightly. They mark, okay, so this is your C dash. So I shall just erase this. Okay, so this is your C dash. And now you are able to mark C dash and B dash. All right, and this is at 50 meters and 30 meters. Now the claim is that A, B dash, C dash is similar to A, B, C, and you know why I'm so confident about it. It's because of S, A, S. Now that is because angle A is common and the remaining two sides on either side of angle A are S and S, that is in the same ratio. So by SAS, this similarity is true. Now you can immediately see that all you need to do is measure, I made a small mistake here, this is C dash, measure B dash, C dash, and let's say that it turns out to be 70 meters. All right, so that means that this implies that BC is equal to 100 times 70, that is 7 kilometers. So that's how you figure out BC. And now if you want this angle that I'm referring to here, you just have to measure this angle because they are the corresponding angles of similar triangles. And similarly, if you want to measure this angle here, angle C here, if you want to measure this angle here, then you just have to measure this angle here that I've marked because the two triangles are similar. And in this way, the Tunnel of Samos problem was solved. What I shall do now is direct you to better storytelling by referring you to the book as well as the video of Tom Apostol. So that's it for now. Please do enjoy the video and the book. See you. Bye.